Okay, hello there. This is Mr. Leader's Cutting Edge YouTube channel, and I'm going to tell you today about some applications of vector problems. So this is an example from your book that I'll take you through, and a lot of vector problems have to do with airplanes or cables and tensions and things like that. So this is kind of just how you write something that where you're given an angle and a velocity, how you write that in component form. So with this one, it says find the component form of the vector that represents the velocity of an airplane descending at a speed of 100 miles per hour. So this can be written in the angle form, in the trigonometric form, as V equals the magnitude, which in this case is 100, okay, times the cosine of 210, because that's degrees from horizontal in the I direction, plus 100 times sine of 210 in the J direction. Okay, and that's in degrees, and you want to be in degree mode for this one. Okay, I could have written it as 100 times the quantity cosine 210i plus sine 210j, but this is quicker. So then it says for this problem, it does say an angle of 30 degrees, which means that it's going descending at a speed that this angle here is 30 degrees, but that means from horizontal it's 210 degrees. Okay, so to put this into component form, and in this case they're calling component form IJ form, and all you have to do is figure out what the cosine of 110 is. So I mean 210. So the cosine of 210 is when the reference angle is 30 degrees, and that's a point on the unit circle, and the cosine of 210 is negative root of 3 over 2, and that's in the I direction, and sine of 210 is negative 1/2, so that's plus 100 times negative 1/2 in the J direction, and when you simplify that you get negative 50 root of 3i minus 50j, and that's how you write this this vector in component form. An airplane, find that direction. So in other words, this airplane is, when it's going 100 miles per hour at an angle of 30 degrees downward, it's going across at negative 50 root 3, whatever that comes out to be, and down at a rate of negative 50j. Okay? So an application of that is when you have a bearing problem where you have a couple different things going on. So I'm going to make XY axis right here. Okay. And then a plane has a set bearing of south. Always draw a picture because it helps you think about the problem. Plane has a set a bearing of south 60 east at 600 miles an hour. So I would draw a picture of that vector without arrows on it. I mean with arrows going in one direction. So this is the plane going south 60 degrees each, which means it would be going like that. Let's do that again because that doesn't look like 60 degrees. So about there. Okay. And that means that this angle here is 60 degrees, which means that the entire angle is 180, 270 plus 60. So this angle from here to here would be 240 degrees. And he's going this way at 600 miles per hour. Okay? So usually what happens is there's a wind going. But there is a wind blowing in the direction north 45 degrees east at 80 miles per hour. So what I would do is write, since we add vectors, the tip of one to the tail of the next one, I would make another little mini xy axis right at the tip of this vector, so you could see what north 45 degrees east looks like, okay? And then north 45 degrees east means 45 degrees east of north. So that's a smaller vector because it's going 80 miles an hour, so the length kind of represents the speed of the vector. So I'm going to try to draw one in there, and that angle there is 45 degrees, and then the resultant vector, which is what you're looking for, which is the resultant speed, and the direction is going to look like this one from, oops, I want my line. Yeah, that's right. So I want my line tool. I want them to be a different color. How about that color? Okay, and he's going to go from, so the plane is actually going that way, okay? And that's the resultant speed. Whoops, no arrows on the end of my lines. I don't want arrows. There we go. Go back. So here's your resultant vector, and he's going this way at 80 miles per hour. And you know that this is 45 degrees. So if you were pretty tricky, you could just use law of cosines, because this is 685, and the angle between them you could figure out using geometry, because that's 60 there, so this one would have to be 60 here, so that total angle there is 105. And then you could use law of cosines to find r, but in this case they want you to use do it by adding together vectors. Okay, so we're going to call this the we'll call this the plane speed, and we'll call this the wind speed, and we'll just call this the r speed, the resultant vector. So the plane speed, wind speed, r speed. So vector p, and we'll call those all p's, p is equal to the magnitude, which is 600, times, in component form, or in trig form, cosine of this angle is 240 degrees, okay? So 240 degrees in the I direction plus sine of 240 degrees in the j direction. So that's the plane speed. The wind speed, since this is a 45 degree angle, and if I started that's just 45 degrees from the x-axis, and so the wind speed is going 80 miles per hour cosine of 45 in the I direction plus sine of 45 in the j direction. Okay. So now we're going to use the distributive property here, and we're going to simplify cosine of 240, and the cosine of 240 is 600. Cosine of 240 would put me 6 degrees past there, so that means that this angle, the reference angle, would be 30 degrees, so that means it's root of 3 over 2 positive. Okay, so it's 600 root of 3 over 2I, and the sine of 240 is, whoops, that's not 240, is it? That's 270 plus 60, which would be 330. Sorry about that. It's okay. Hopefully those of you in the viewing audience caught that mistake. Okay? So that's 330. Cosine of 330 is positive square root of 3 over 2. And the sine of 330 is a negative 1/2. So I'm going to go plus 600. I distributed through the 600 times negative 1/2 in the j direction. Okay, so that's my plane speed. And my wind speed is going to be 80 times the cosine of 45, which is root of 2 over 2 in the I direction, plus the sine of 45, which is also root of 2 over 2 in the j direction. Okay, and then I'm going to simplify both of these. So the plane speed is 300 root of 3I minus 300j. And the wind speed is 40 root of 2I plus, oops, that should be a j, plus 40 root of 2j. And now what I'm going to do is I want the resultant, the speed of the resultant vector. So I am going to take the, first I'm going to add those two together, and that would give me the resultant vector. And then I'm going to find the magnitude of those, that resultant vector, and that will give me the speed of the plane. So the resultant vector is going to be, you just add up the I components, 300 root of 3 plus 40 root of 2, all that in the I direction, plus negative 300 plus 40 root of 2 in the j direction. And what you want is the magnitude of that. And the way you take the magnitude is this whole piece of stuff squared plus this whole piece of stuff squared, and then you square root it. So that's going to be the square root, and this is where you got to be a little careful. You're going to do a big square root thingy there. 300 root of 3 plus 40 root of 2 quantity squared. That's the x part, the x components. Plus, I'm going to call this 40, oops, I'm going to call this 40 root of 2 minus 300 quantity squared in the j direction, okay? And then I just plug that big chunk into my calculator, and I get that r is equal to, well, let's do it as long as I'm here and I got time. Let's grab that calculator. Okay, so I am going to close this. U always in front. Get rid of this. Move this. So here I go. So I'm gonna first. I'm just gonna compute this 300. Oops, I need some parentheses. Let's clear everything out. In parentheses, 300 second square root of 3 plus 40. Oops, I gotta get rid of that. (300 square root of 3). I have to get outside of the box. Plus 40. Okay. All right, I'm back. So where were we? We were doing some math here. Okay. So I was finding the magnitude of this. I forgot. So I'm going to close that parentheses. I am going to square that quantity. Okay. And then I am going to take Then I'm going to take 40 root of 2 minus 300, so plus 40, got to use parentheses again, plus 40 second square root of 2, arrow over, so I'm out of the square root box, minus 300. And I close the parentheses. I'm going to square it. I'm going to add those two things together. Gives me some big, huge number. And then I'm going to take the square root of that number, second square root, second answer. And that will give me 610.26 miles an hour, which is how fast the plane is going. I think I did that right. Okay. So then once you have done that, then they also want the direction. So to find the direction, what I would do is just, so you want to find really this angle right here, but the way you could find that angle right there, because you want it as a bearing, you could find this angle right there. I think the quickest way is just to use, let's see, sine of that is to that, as sine of this is to that. You could use a lot of sines. You could use a lot of cosines since you know all three things, or you could also use the fact that the inverse tangent, or that tangent of theta is equal to b over a. Okay, in this case, and so you want the direction of this resultant vector right here, so it's this divided by this. So tangent of theta is b over a. So if I take the inverse tangent of 40 root of 2 minus 300 divided by 300 root of 3 plus 40 root of 2. I could do that on my calculator, and I get that that angle is approximate. Oh, that's very messed up. This should have been a root of 3. Okay, we're okay. And so 40 root of 3 plus 40 root. I get that that angle is about, if I take the inverse tangent of that, I get negative 22.91 degrees. So what that means is from here, that means that from here to here, right, that angle is negative 22.91 degrees, but you want this as a bearing, okay? So if I subtract that, so really what I want is degrees from south to here. So if I subtract 22.91 from 90, I get 67 degrees. So that angle there is 67 degrees, but you call that south, 67 degrees east as a bearing. Okay? So that's a lot of work. Can you sign it with, if you know how to solve it with a lot of cosines, you can do that, but that's how you do it with vectors. All right? Okay. Thanks. Next problem that you're going to see is called the static equilibrium problem. And I'll just talk about it. I'm not going to solve it because those can get pretty ugly with the algebra. And but I'm at least going to set this up for you. So to do this problem, you want the static equilibrium, if this box is has a weight of 20,240 pounds and it's not moving anywhere, then these cables are in static equilibrium. And the basis for this problem, since it's not moving left or right, the x component left and right are equal to each other, and the y components, the two y components of these cables has to equal the vertical component of this box, which is going straight down at 2,240 pounds. So in the first instance, what that means is that 20,240, okay, is equal to, that's in the negative j direction, is equal to the is equal to some force. We'll call this force 1 over here, force 1, and we'll call this force 2, because what they want to know is find the tension in each cable. So it's equal to force 1 times the cosine of 44.5, whoops, sine of 44.5 in the j direction, plus force 2 and plus force 2 times the sine of this angle from here to here is not 23.5, it's 24.3, it's 180 minus 24.3. So force 2 times the sine of 180 minus 24.3 is 155.7, I believe. Okay, and so there's your one equation. Okay, so because this force going straight down, right, has got to be equal to these forces going up, because the box is not moving up or down. So you could set those, so you have 20,240 is equal to, and since these are both the j components, you could call that force 1, you could just get rid of the letters. Okay, so it's force 1 times the sine of 44.5 plus force 2 times the sine of 155.7. Okay, now the other thing that's got to be true, since the box is not moving either way, left or right, you also know that the horizontal components have to be equal. And the horizontal component on this cable is force 1, whatever, because that's the magnitude of the force on that cable. Force 1 times the cosine of 44.5 plus, or is got to be equal to, force 2 times the cosine of, is got to be equal to force 2 times the cosine of 155.7, okay, because that's going to give you the force going that way, and that's going to give you the force going that way. Actually, mistake, those two added together has got to be equal to 0, because these two added together, this is going to give you a negative number, is going to give you a positive number because of cosine of an obtuse angle, and when I bring this onto this side, it becomes negative. So now what you do is you solve for either force 1 or force 2, and you plug it into this equation, and you solve for force 1 and you solve for force 2. Okay, and I'll let you try to do that for home, but that's the basic way you set that one up. The last one is a boat problem, and the way you do one of these, it's like a boat on a ramp. And the trick with a boat on a ramp, it says a force of 600 pounds is required to pull a boat up the ramp. So there's a force going this way at 600, but it turns out that that force is equivalent. I could break down this force going straight down, okay? I could break up this force, which is going straight down, into two components, one going this way at 600, okay, and one going this way and one going this way. But I know this is 15 degrees, and how do you know that's 15 degrees? because they tell you that the boat's on a 15-degree incline. Okay, and so if this is 15 based on this right triangle here, see this right triangle right here, this angle would have to be 75, and this is 90. So that makes this little angle right here 15 degrees, because these have to add up to 180, these three. And then that would make this 75 as well. So what you have is some similar triangles right there. And then you can just use right triangle trig to figure out, because to find the combined weight of the boat and the trailer. So what they're looking at is this force going straight down like that. Okay, and since this is the hypotenuse of this right triangle, you can just, and this is the opposite side, and this is the hypotenuse side, you can just say that the sine of 15 degrees is equal to 600 pounds, okay, because that's the force pulling the boat up the ramp. This is the force pulling the weight of the boat and the trailer going down. So sine of 15 degrees is equal to 600 opposite over hypotenuse, which is what we want. And that's we could call that, I don't know, the weight over the weight of the boat, the combined weight of the boat and the trailer. And then you can solve this algebraically. Multiply both sides by W, divide both sides by sine of 15, and you get W equals 600 divided by sine of 15. And if I do that on my calculator, I get 2,318 pounds. 2,318 pounds is how much the boat and the trailer weigh together. If it takes 600 pounds to put up here. Okay, so that's the end. Hope you learned something. That static equilibrium problem, it's hard to set up, but try to do it. Okay, and these problems could be a little tricky, and that's the other one, breaking down an airplane moving into component form. And you can look at these, and that's it. Okay, goodbye.